Okay, this is Lab 3, Black Hole and Orbits. The purpose of this lab for Part 1 was to find the mass of a black hole given the mass of a star orbiting it and the forces acting on that star. And for Part 2 was to come up with a model in which a spaceship orbits a moon and a star at a figure-8 orbit without running into the moon or the star. The fundamental physics principles used in this lab were Newton's second law, momentum, and the gravitational force. A brief overview of the results. In Part 1, the mass of our black hole was much bigger than the star and anything else in our system. And in Part 2, we were able to successfully create the figure-8 orbit without running into anything. The main physics ideas were that the net force is equal to the change in momentum with a change in time, the velocity and position updates, which the equations are listed there, and the gravitational force equation. The system in Part 1 was the star, and in Part 2 it was the rocket. The surroundings in Part 1 was the black hole, and Part 2 was the black hole, the star, and the moon. The initial conditions, in each scenario we have an object that is in the orbital path of another object, and we're given the mass of the star through the instructions of the lab. Here's my code for Part 1. The lines I changed are highlighted, so I added the star's mass, the delta t, which was a year, the initial momentum and final momentum, also the change in velocity and the change in momentum. And then we use that F net is equal to the change in momentum over the change in time. And then we could find from that P hat, the magnitude of P, and the parallel and perpendicular forces acting on the star. We also had to use the position update, and then we had to define the arrows that are on our model that show the magnitude and direction of each of the forces. Here are the results from Part 1. The average of the masses calculated was 9.55 times 10 to the 33rd, so obviously very much greater than anything else in our system. The star orbits the black hole in the path shown in green, and the forces acting on the star are represented by the arrows coming off of the star. This is my code for Part 2. Up at the top, the X and Y speeds, lines 55 and 56, are shown that I found. Then I also had to find the forces acting on the planet and on the ship, and those are also highlighted. And then I used the velocity and position updates to update the moon velocity and the ship velocity. So here is the output of my code. We were able to create the orbit without running into the moon or the star. The rocket's orbit is shown in the magenta color, while the orbit of the moon is shown in the cyan color. Possible sources of error in this lab. For Part 1, we could have incorrect calculations for the forces acting on the star, because we could maybe not account for another mass that has gravitational force acting on it, or something like that. And in Part 2, we could have the incorrect speeds added to the code in the beginning. There is not like one right answer for this part of the lab, so we could have seen different orbital path had we used different speeds in the beginning of our code. What does it mean? So the what does it mean question was think about the rate of change, what the rate of change in momentum means, and what net force means in terms of the things you can observe and measure in this scenario. So the rate of change in the momentum is the net force in this scenario. That is what we use for most of our calculations in Part 1. We were relying on that principle to derive the forces acting on the star. And then the net force is equal to the parallel force plus the perpendicular force. We also use this in Part 1 of our lab for the net force on the star to solve for the perpendicular force. The what if question was, the imaginary system has a black hole, a star, a planet, and a moon. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? Think about all the interactions in the system. Would there be any dominant interactions, or would they all contribute more or less equally? So all of the forces in the scenario would have to be modeled. All the forces modeled in Part 2, like meaning the forces of the moon on the rocket and the planet on the moon, or the planet on the rocket, and plus the forces that the black hole exerts on each component. So the gravitational force that the black hole would exert on each of the different components, the star, the moon, and the rocket. And then the black hole would have dominant interactions in this scenario because of its large mass. Remember, the gravitational equation is negative g/m over r. So the bigger m you have, the bigger mass you have, the stronger the gravitational force would be. Okay, thank you for watching. Bye.